How is that? Can you hear me now? Like getting the VU meter at least looks quite loud. Hopefully that works. Thank you for pointing that out. I'm very sorry. I hadn't noticed that one. Not quite sure what's going on there, but never mind. It's resolved now. So, right, yes. I'm going to give ground reference, and they can both share. They're good friends. And we've got CAN low is the white one, so that's going on the yellow channel of the scope. CAN high is the blue, that's going on the blue channel of the scope. Just like that. And then if I show you the scope and zoom it in, right, so okay, that looks good for an idle CAN bus. Let's set up the serial decode. So we've got signals. The difference. Right, okay, so CAN high is channel 1, I think it was. The baud rate is 250 kbits. And then let's set the trigger to be about a frame on CAN 1. Okay. Oh no, oh, I updated the firmware, that's why this has all gone wonky. Here it is, there we go. Okay. Right. So if I was to send a CAN message on this bus, do we see anything? The answer is no. Oh, I know exactly what that's about. That is because I need to turn off the safe mode. Right, these devices are kind of designed to be a little bit safe, which means that we need to put a special key in there so that they will not talk, or before they'll talk on the bus. So once we give it the key, they're allowed to talk, basically. Just show you my screen, sorry, so you can see what I'm doing. Oh dear. This is CAN 1. No, that's fine. Oh dear. Okay, 1 second, excuse me, let me go and read my documentation. That is the correct key. Let's see why it would be different. Let me restart this device. Oh, that's better. There we go. And then bus mode is normal. Okay, that's all much better. IP link set to 250k, and I think I was using ifconfig to turn it on, and then CAN send 5555. And what do you reckon? Any messages? No. So this is the issue I was trying to battle with before I came live. I'm not entirely sure what's going on here. Oh, there is a message. Oh, there's loads of messages. But they're coming out at the wrong bit rate, maybe? So if I just come in on here, measure the bit time that we're seeing. That's about 250k. That's fine. Serial, CAN, signals 250k bit. Threshold, oh, this is CAN low, whoops. So it needs to be CAN, there we go, there we go. Much better. There's the message. There's the trigger, and there's the auto trigger mode. Okay, I've this week I've got the scope connected via HDMI, so hopefully we should have a much better refresh rate on the stream, and it won't be quite so icky to look at or slow to look at. Hello, Oryxnumlum. Thank you for joining, good to see you. Apologies for probably destroying your name there. Right, let's connect that to the other system, which is then going to acknowledge this message and make it go away. Apologies for not getting this all quite as sorted as I had hoped to before the stream. So I'm going to take the blue and white again, drag them off to another board which is out of shot, which will just acknowledge it. This board isn't behaving quite right at the moment. It's being a bit naughty on the CAN bus and just splurging because no one's acknowledging it. It's trying to send it over and over again. And that's not okay really, but it is what it is. Hopefully as soon as I connect it up to this one, we'll be good to go. And I can never remember which way around the signals go. Nope, not that way. Not that way either. Oh, this is annoying. Alright, let me just have a look at another reference board I've got here. Confirm which way these are. Low is white. I've got CAN low connected to white. That looks all okay. CAN low comes from here into there. Yep, that all looks good. What a retry indeed, yeah. This is really, really annoying. There's the scope in tiny mode. I'll show you the scope in big mode. Right, so I'll turn the bitrate to 250k. Bring the interface up and try and send a message. And we see nothing. That's unexpected. Oh, we've got to do the silent mode again. Okay, that into. Oh, come on. A bit fragile, this device, unfortunately. Right, so set it to 250k bit. Bring the interface up, disable silent mode, there we go, and send a message. Boop. There we go, over and over again. Hi Durand. What are the two 4-pin large chips? Are we looking at these ones here? They are opto-isolated photo transistors, basically. So they provide for the termination, so you can turn them on and off without being electrically connected or near the CAN bus itself. I'll just show you the schematic quickly. So in the hierarchical view, there we go. It's this chappy here, termination resistor, or transistor. It just switches that 120 ohm termination in and out. You can't see that though. There we go. Right, meanwhile, what is going on here? We get the scope back. It's sending over and over again. Bus mode is normal. Is this set to the wrong board rate? Bit rate, whatever you want to call it. Sorry, I'm doing this off screen on this other system. Yes, I think it might be actually. Just grab that. I acknowledged it. Still seems a bit fuzzy. Oh, this is annoying. Oh, hang on. I just connected it to the wrong CAN bus on this other board. Is that the simple solution? There it is. Oh, there we go. Sorry, everybody. So, back to it. Okay, we can send our messages. There's a 5555, and I can do a, what should we do? AA, which will look a little bit different, like that. There we go. It's being acknowledged, it's being removed off the bus, and I can see it coming through on the other side, which is fantastic. So now we can finally get around to working with Glasgow again. I did want that view, there we go. So Glasgow is here, and I need to plug it in. And as of last week, we got to the point where we were kind of seeing something, but it wasn't looking very good, and it wasn't the data that we were expecting to see, and yucky, 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 ick, 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 etc. Okay, so get rid of one of those, and here we are. So we can do a Glasgow run sniff. Oh, sorry, CAN sniff. Now, I don't quite remember how to run this, so let's just check. We're doing everything I think is the defaults. The bit rate is 250k, which is correct. So we can just do -v5, turn it on. And hopefully it's okay with my rework. Oh, found two devices. This one. And that says no. Oh, yes, right. That's where is it? Where is it? FPGA toolchain bin. I thought I'd added that to my path already. This one. Go. There we go. Building. Looks okay so far. And if I now send a message, what do we see? We see some garbage. Right. Okay, we're back to where we were last week. Not last week, I think the week before. I had to cancel last week's, I think. Okie dokie. Oops, what we're doing, projects, Glasgow CAN. It's funny how muscle memory works, isn't it? Into Glasgow Applets, no, Glasgow software, Glasgow Applets. Interface CAN sniff, there we go. So this is the applet. What was the rework I mentioned? We found the other week that, so this is the board layout, that this pin here, number 5, I ordered the part which requires that to be connected to a supply voltage, and I had designed for a part which doesn't mind if it's not connected to a supply. So pin 5 should be connected, so I've wired that up, and I don't think you can quite see it on camera here, but there's just in here, there's a little orange wire. So that was a little bit of rework that I did. And then we also found that the termination LED was shorted underneath. So I have replaced that as well, just for good measure. So that should now work, which is, fingers crossed, the right way to do it. Twitch 0xne, next Glasgow shipments are only at August. Oh. So I presume you're referring to the crowd supply campaign, is that right? So that is actually done incredibly well. Oh, go away. So as I'm sure most people who are watching are aware, Peter and the 1-Bit Squared team have been bringing the Glasgow to mass production. They have 1,416 backers, and it's now moved over into pre-order. So if you want one, do come along. I'll put the link to that in the chat. Do come along here and just order one. There's a nice aluminium case as well, etc., etc. So yeah, have a look there. And I have a feeling that it's done a lot better than was expected, which means that, as you say, the shipments might be delayed somewhat, unfortunately. So that was the rework. That's the crowd supply campaign. We can now hopefully come back to the applet itself. Now, the way the way that CAN works is like this. So you have it's kind of a pseudo differential signal. It's not actually rail to rail, but they idle together. So as you see on the scope there, if I send another message just to trigger the refresh, there we go. So they idle together on the left and right hand side of that image, and then they separate to sort of convey their data. And that separation, so that when they're together, it's called the recessive state, and when they're separated, so the blue goes up and the yellow goes down, that's called the dominant state. And CAN makes use of this to convey the data that it's sending. Now, we were looking at this, trying to get everything going previously, and there are some things that we need to be careful of. So first of all, the start bit is always a dominant state. And dominant state is 0, so you trigger off that. Then for each bit, there's actually what they call a time quanta sort of separation. Here it is, which means that you get the beginning of the bit, then there's a time period dedicated specifically to synchronization and the propagation of the signal through the network. And then you have phase 1 and phase 2, and this allows you to shift the sample point left and right. Typically, the sample point will be, as shown here, sort of towards the end of the bit time, which means that if you're comparing something like UART, you would trigger off the beginning of the bit and then you'd sample it about halfway through, and you'd effectively be offset by 90 degrees for the rest of the 180, 90 degrees, half a bit time for the rest of the packet, the frame, word, whatever you want to call it. So yeah, with CAN, it's slightly more complex in that you've got to aim for this sample point. So we've taken care of that here in the MyGen. Let's come down to here, I think. Nope. Where is it? So we've got this RX trigger signal, which we are using. So that sets everything off. And then we've got the bit phase 1, bit phase 2. So at the end of bit phase 1, you take your sample, and then you need to wait for the rest of the bit time before you start again. So if I come back here, this is the trigger point, and then we'll actually have the sample point sort of towards the end of that bit time, and then we'll wait for the next bit time, have a sample point there, and the next one, etc., etc. In terms of knowing when you're done, that's something that you can't tell from here. So at the end of the bit time, we check this RX run flag, and that tells us if we want to carry on receiving data or if we think we're finished. So if that indicates that we're finished, then it just goes back to the idle state at the top. Otherwise, it comes to the bit done state, resets the counter, and heads back into bit phase 1. I could probably clean that up a bit by doing that. That's nice, isn't it? Perhaps not quite so clear to read, but I think that'll do. Okay. Now, part of the other problem that we've got, so this is handling the sample point, this module here, the low-level module. I should probably call it something different, but that handles the sample point. And the next thing we've got to do, which we weren't taking care of at all previously, is bit stuffing. Now, with CAN, because it's sort of designed for a reliable environment, you get all sorts of safety mechanisms kicking in. And some of the safety mechanisms are actually in the electronic and the hardware level. So the transceiver here is, it will actually remove you. If you try and assert dominance on the line for too long, it will actually remove you from the line so that you can't lock up the entire bus. So that's taken care of in silicon. It's a really low level protection scheme. So if your processor asserts the transmit line and then locks up and leaves it asserted for more than, I think it's something like 100 milliseconds, this will just kick you off the bus. In addition to that, you've got other things like bit stuffing, and they are here to work in tandem basically with what I was saying just now about the transceiver. So if, for example, your micro asserted the transmit line, it went dominant on the bus, and then it wanted to send 8 bits, for example. So we've got 1, 2, 3, 4, 5, 6, or 7 bits. So there's 7 bits in this example. If you want to send 7 bits, then actually you're going to violate that threshold. You're going to try and be asserted on the bus for too long, and that is not acceptable. So to take care of that, what they do is they actually insert this purple stuffed bit. And that's just a bit of the opposite polarity, which puts a transition on the bus. And I think, pretty sure, that this happens for the opposite as well. So if, in this case, you're trying to send lots of zeros, and so you need to insert a 1. But I think it also happens if you're trying to send lots of 1s, you need to insert a 0. Because as you can see at the end here, at the end of the frame, that's lots of 1s, but if you wanted to send lots, then you've got to sort of make it clear that you're still talking, you're still on the bus. Okay, so this is something that we haven't addressed yet. Do feel free to ask any questions, by the way, as we're going along. If I'm going too fast or skipping over things that you'd like to know about, please do ask. Okay, so we've taken care of the bit phase and the sample point. The next thing that we haven't done at all is to take care of the stuffing. Now, if we come back here and just receive a single frame of 5555, you'll see there's quite a lot of garbage, FFs in there, and this could be for a number of reasons. It could potentially actually be that we're sampling at the wrong point. It could be that we're not taking care of bit stuffing properly. It could be all sorts of things. So these received frames, or the received bytes here, they're just completely wrong. So we've got to back off and have a look at what we're doing. I think the best thing to do right now probably is to get some confidence in our sample points. So what I'm going to do is hook up another wire and another scope channel to the Glasgow so that we can see this trigger happening. Let me just remind myself where that trigger signal actually is. It's on RX trigger, which I don't think is right. So that starts the whole thing. RX ready, that's the one we want to watch. Okay. So what we can do now is add another signal to the applet. Let's just call it debug, what are we going to call it? Debug sample point, SP. Okay, so we can pass that through. So that gets handled automatically by the various Glasgow infrastructure. So just by adding it to this tuple here, we've automatically defined the arguments that will get produced on the command line, and then we're also passing that pin through into the applet. So if we come through into the CAN subtarget applet here, or the module, we've got this pads variable, and in this pads variable we're going to have, let's actually put it down here. I know we don't keep it, so let's keep it here then. We are going to have this new one, which is the debug SP pin. So let's just scroll up. Yeah, so debug SP _ T. And then that's got the output enable, which we're going to set to 1. Oops. And also the output, which we now want to set to be equal to that RX ready signal. And I'm actually going to have to move this into the module, and I'm going to keep the pads just temporarily so that we can reference them down here. Oops. Okay, so the low-level module then has this RX ready signal, which RX ready, which we're going to put in there. M.D.combinational, and we're going to add these two wirings up. There we go. So I think that should work. If we now quit our applet and do -- help, we should see, here we go, we've got the pin debug SP. Now, we actually want to put this on a specific pin. We don't want to let it default, because that will, as you can probably see from here, that will put it across this ribbon cable and then into one of the Glasgow channels here. So what we actually want to do is put that on a specific pin. Because we're running this in 2-port mode, so the port spec is AB, the pins are numbered 0 through to 7 and then 8 through to 15. So if we go for pin 8, for example, then that should put it in the right place so that we can see it. It has no pin debug -SP. I think let's get rid of that dash just because I'm not sure how to handle it. Debug SP. We then need to take care of it here as well. Debug SP. And get rid of that one as well. RX ready is not defined. That's because I need to low level .rx ready. Okay. So I'm just going to grab another scope probe. If I can find them, here they are. It's a bit of a bomb site in here at the moment. Okay, get a boot for it. There we go, and so what we're going to do is connect that up to, where have my wires gone? Oh, I put them here. Let's use green. Okay, I said 8, and that is B0, which is on the far right hand side here. So I'm just going to use that pin there and put that straight into the end of a scope probe. Okay, now hopefully on the scope we should see that representing our bit timing. I'll need to turn it on. It's got very noisy all of a sudden. That noise actually looks like the bit time signal that we're trying to see, so I might need to add some more grounds to this. There we go. What does that look like? Not great, to be honest. Looks like an impulse for some reason. Put another ground on that. Hopefully that'll get cleaner. Use the corner just there. Ooh, is that okay? Oh, that nose has fallen off. These noses are a bit frustrating sometimes to deal with. Okay, it's a bit cleaner, but it's still not quite what we were expecting. I'll tell you what, the downside of using HDMI to capture the scope is that I can't point at it now. So if I pointed it here instead, can you see that okay? It does scale, so that's nice. Can you see my cursor? I think you can just about, can you? What we have is the bit time is here, and the sample point is actually pretty much exactly where that bit of whatever that is, noise is. However, we're expecting the RX ready to go high here, and then go low again here, and then go high here, and then low again there. High at the sample point, low at the end of the bit time. So something's not quite right in the code. What do we think it might be? Ah, okay. So it's actually not doing... it's doing exactly what I told it to do, which is not what I wanted it to do, which is fantastical. So I'm going to do with that as FSM, and then MD combinational self Rx ready equals, I think it's ongoing. Yes, it is. FSM dot ongoing bit phase 2. So what we're saying here is that while we're in bit phase 2, assert the Rx ready pin. I think that'll be much better. Let's get the scope back so we can see it hopefully doing its thing. Okay, so if we send a message, oh, that's better. Much better. Oops, what am I doing? There we go. That's exactly what we wanted to see. Brilliant. So it goes high on the starting, or the sample point, and it goes low at the end of the bit time. Okay. Let's get the whole frame in shot. Oh, there's more of it. There we go. Now, the other thing that we also see is that it carries on long after the end of the frame is complete, which means that we're doing something wrong. And if we have a look at the code, so it basically latches itself. When it's in the idle state, when it sees the bus go into the dominant state, it starts, and then it keeps going while that Rx run signal is asserted. So if we now dig into that Rx run signal here, while we are not idle, continue running is basically what we're saying. And so now we need to figure out why we're not going idle correctly. If we look at the frame outline here, we've got the arbitration field, which consists of the address or the ID and the remote request. So if we just confirm that here, the arbitration ID is 11 bits long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is correct. Okay, let's just check that counter is actually operating correctly. So on the Rx ready pulse, when that rises, oh, hang on, that's an if, that's not a clock edge, is it? So we want that to be the rising edge of, not an if. Alternatively, potentially we could latch it. How to handle that one? Because at the moment the clock is running at something like 48 megahertz. So all of the time at the second half of that bit phase 2, that entire duration is going to be clocking through this, which is just wrong. So it's going to be getting lots and lots of data where it should only be seeing a few bits. Makes me wonder if actually the previous setup was correct. In that previously we were, sorry, covering up with the scope, previously we were setting it high for a single cycle. Why don't we undo that and just see what happens in terms of, does it run on past the end of the frame like it's currently doing? So let's put that back in there. Restart the applet. and send a message. Boop. Yes, it does. How far past does it go? I think, judging by the amount of data we're getting, so that is... That's 15 bytes we're receiving there. If we then put this back in, we can just demonstrate the issue a little bit more clearly. Ooh, yes, a whole screen full of data, or multiple screens. 1, 2, 3, 4, 5, 6, 7, 8 screens worth of data. So that's exactly the problem. That's not good. Let's leave it there then. So if RX ready is asserted, then we need to set the counter to 8, arbitration ID, reset it to 0. Okay, now this comes on to something else which I think I might have got wrong last week, which is the bit ordering. So when you're catting things together, concatenation of signals, I think I get this wrong very easily, unfortunately. Haven't burned it into my head yet. Why don't we do a little experiment just to see if that's okay? So I'm just going to make a new state machine here, and in this state machine we are going to just shift 5 bits or in, something like that. Hey AnyMouse, we are working on a Glasgow CAN add-on. So this is a Glasgow Interface Explorer, I'm not sure if you've seen it around, and this is then a CAN add-on board that I've designed to allow us to interface with CAN buses. And we're working on the NMygen, so that's the FPGA code to make this work, which runs in the Glasgow's FPGA. If you have any questions, please feel free to ask. I'm happy to answer them. Duran, do I think it's possible to use the applet without the PHY if the bus is limited to 5 volts? Not really. Because of the way CAN works, I was showing you earlier here, and it's actually probably clearer on the scope potentially. Because of the way it works, you've got the signals idling at sort of the midpoint, and then they get asserted one way and the other way, and then they idle again. That sort of midpoint idling is potentially a little bit tricky to deal with. And then you've also got the other bits and bobs going on there. I suppose you probably could make it work if you sort of rely on everyone else on the bus to bring that idle point together. I wouldn't like to do it though. You might get away with it. Feel free to have a go. I'm not going to stop you. Maybe don't do it on your car. Maybe do it on a desk instead. Right, so A, B, C, D, and I think we'll stop there. I'm just going to shift some bits in. Done. So in setup, we're going to do going to take something like the arb ID and set that to 0. Then arb ID equals, and we're going to use cat here just to try and prove our stuff out. Oops, so we do cat, and we're going to take the arb ID 1 to the end, so that there should be not the least significant bit, but the one up, which in my mind is the far right. and a constant 1. I think size 1 will do that. Probably won't actually, it's width probably, isn't it? Okay, so that should put a 1 in the right hand slot. And then we're going to put a 0 in. And then we're going to put a 1 in. And then here we're going to write that out to the FIFO, which is, where is it? Here it is. Oops. No, we're going to take the lowest 8 bits of the arbitrary or the arbitration field and send that to the host. Okay, so what do we expect? Does that build? It doesn't build. Setup. It's got a semicolon on the end of it. Okay, better. Nope. Oh, return M. Okay. Doesn't like width. Is it size? No. Sure, I've got a constant here somewhere. Oh, okay, I have to give it the shape. So that'll be unsigned 1 bit. We got enough brackets still, yes. Okie dokie. How does that work? So what do we expect? We expect 0 with a 1 shifted in, then a 0, then a 0, then a 1. And that would be a hex 05 if this works out. Oh, that's a sync. Let's do a combinational there. Okay, so 0 comes out. That's not what we expect at all. Let us do that straight to D. And in this case, we should see hex 01. Which we don't. Why is that? It's an 11-bit signal. I think const 1 needs to go here, which at least gives it some consistency with the array indexing, or the list indexing, whatever you want to call it. Yes, okay. Let's put that at the front. That looks... Oh, I put it in front of the cat, whoops. Oh, that's why it looks wrong. There we go. So if I then do B, and I then do the final one, just here, now we should get a hex 05 out. Which we don't, we get an 01. Why do we get an 01? A, B, C, D. Oops, so this should be a hex 7. No. What's going on here then? I'm kind of tempted to put zeros in there. and I'd expect to get an 01 out of that. Which we do. And I then want to do a const 0 like that. And that should be a hex 2, right? Yes. Okay, and if I change that, oh sorry, add in front of that, then we should get a hex 5. Yes, okay. And if I turn that 1 to a 0, that should be 1, 2, 4, hex 4. Which it is, okay. Now, this means that, I'm going to write it down so that I can refer to it. Yeah, I'm Hard Crash, I'm struggling to get the order of the bits correct in my head for a cat versus bit indexing versus whatever else. So cat will concatenate 0, 0, 0, or let's do 1, 0, 1 into 0x05, right? And that, so x1 colon nothing, will strip the first bit off. So that also means that that address is the least significant bit, I think. Okay, so if we now try and prove that more, make this a 1, get rid of these, and put back in the arb id 1 colon nothing. That then, paired with the other two, so once here, and once here, that should shift 3 bits in to the lowest 3 bits of that arb id field, and then we should send a palindrome. It is indeed. And that should then send that as a hex 07, right? But it wasn't behaving earlier. See? Hex 01. Oh, you're joking. Really? You want -1 in there? So are these two statements correct here, Hard Crash? So x0 is the least significant bit, or x -1 is the least significant bit? Yeah, helps to have people who know what they're doing around, doesn't it? I could have sworn that was the other way up. That was a guess. I'll give you the credit anyway. I'm happy to do that. Okay. That means that x0 addresses the most significant bit. Most significant bit, right? And if I turn this to a 0, we should get a hex 5 out. And then we can come back and rewrite all of my other code so that it follows the rules which are correct instead of the rules which are wrong that I had locked in my head for some reason. Okay, there we go. I'm going to keep these at the top of the file for reference forever and ever. We can get rid of this. Yeah, me too. I just couldn't quite reason about it. So thank you for your speculation. It was quite right. Okay, that means that here, I'm going to keep these actually as well. Oops. this I'm going to keep for reference. X equals cat1 x minus 1 will shift left and insert 1 in LSB. Yes, I think I'm just going to keep that there. Okay, now we can actually refer to this and get everything working, hopefully. First things first, on the start of frame, reset everything. We've got 11 bits and the arbitration ID gets set to 0. Don't copy the comment with a typo everywhere. Is this one correct? I think that's correct. Oh dear. Right, okay. Here, immediately, this is wrong. So arb ID equals, and we want to put the bus RXI on the bottom, and arb ID to -1 on the top. I don't know why this is really hurting my brain. I think it's that actually cat and bit indexing are both backwards to how I would expect it. Because surely bit 0 is the least significant bit, but also surely the right hand side is the least significant bit. Never mind, ignore me. So that means that this is wrong as well, and that actually we want -8 to the end, right? That arb ID 1 is providing a range of 0 to len -1? Oh, what I've got here, arb ID colon -1. Is that what you're referring to? I think you're right, yeah. It just doesn't feel natural to me, which is why I keep tripping up on it. So here, we're trying to send the least significant 8 bits. Given that this knocks off the least significant 1 bit, so it goes from the most significant down to the least significant -1, as in not quite the least significant. This, I think, should do the same for the least significant 8 bits. Here, we then want to rewrite that. We want the excuse me. We want the arb ID. What do we want here? We want 5. Okay, so we want 5 bits of zeros on top of the final 3 bits that have come in. So that's -3 to the end. And const 0 unsigned 5. I'm getting myself really tangled up here, aren't I? Where's the drawing? Here it is. Okay. We've got the 10 bits, 10 to 0, and the remote request. 10 to 0 form our 11 count. Aha, thank you for the link. Let's just have a quick read of that. Okay. Just like Python arrays, the bits in signals are always ordered in one and only one way. This can cause a bit of confusion for those familiar with indexing in HDL, like probably what I'm doing in my head. While S7 to 0 might seem to extract the 8 least significant bits of a signal, this is not the way Python works, and it is Python that we're programming in. Correct way to extract the 8 least significant bits of a signal would be... No! What? The correct way to extract the 8 least significance of a signal would be 0:8, or just :8. And this is the same way we'd extract the first 8 elements of a Python array. Correct, agreed. So least significant bits there. The first n bits of a signal, when treated like an array of bits, are the n least significant bits. Okay, that's I think what I thought. Which means that this... Yeah, I just can't do numbers, I think, is probably my biggest issue, because that is exactly correct. That's lopping off the top bit and keeping all of the lower bits, isn't it? Okay, right, so the first 8 bits, as it pointed out in that document, is that. Yes, agreed. Next, what we want to do is the first 3 bits, which is going to be that, followed by 5 zeros with there. Okay. Yes. I'm getting more comfortable with this. Why don't we run that quickly and just see what we get? We should have an address of 555. I kind of have a feeling that we're not going to see that. Oh, 5502. We do it again. 5502. Okay. Now, 555 should work. Where are we going? Here, but there. That's right. So that would be 1010 1010 101. So these bits are coming through slightly wrong. I think this might be a pipelining type issue, mightn't it? Maybe? No, because the first 5 fives are coming through okay. Let me just grab this for myself. Hard crash, bit numbering with powers in lists. From BBC, it's been so long, yeah. It's just all backwards, isn't it? I mean, I can completely acknowledge why and understand, and I think I'm getting there. Maybe. Does that mean that all of these are wrong? It does. We'll strip the MSB off. We'll address the LSB, and that will address the MSB, which means that this will shift left and insert in the LSB, which is correct. But let's just clarify that. So OB 0101 will become 1011. Yes. From a high level view. Yeah, everything's backwards, isn't it? Never mind. So long as we get comfortable with it. This probably needs to be 4 because actually we want the first 3 bits. We don't want the first... Yes. We want the first... We want 0 to 3. Oh dear. My poor head. 0, 1, 2. No, we want 0 to 2. Okay, so we do want that to be 3. I'm going to stuff this with, let's do an A. It's going to be 5 bits. That should then turn out to be a 5, right? because of where the nibble boundaries are. Okay. Oh, it's a 5. That's correct. And the fact that that's a 2 means that something's up. Oops. Okay, so 5, 5 does come through, as you would expect, which is good. So the value in R by D is incorrect. And this is because... So the counter goes 11, 10, 9, 8, 7, 6, 5, 4. Yeah. It's delayed by 1, isn't it? So actually we want to know if this is -1. And that's not a good thing to watch out for. So why don't we make this 12, 11 plus 1. Let's make that 4, and let's make that 0. Oops. I'm pretty sure we're getting there. There we go. Oh, it's a... No, hang on. That's a 4. Didn't want a 4. Let me get rid of this A. Wanted a 5. 1, 2, 4. For some reason a 0 came through. If we change this, so let's do A. Oh, I didn't do the thing. It becomes 9, 5. Oh, unexpected. So 5, 5 comes through as 5, 5, 4. 4, 5, 5 comes through as 1, 5, 4. Oh, right, okay. These are most significant bit first. It's the first one which is shifted and the second one which is complete. Okay. That's also part of the problem. So we need 11, 10, and 9 first, and then we need 8, 7, 6, 6, 5, 4, 3, 2, 1, 0. That doesn't add up. It doesn't go from 11, it goes from 10. So 10, 9, 8. That's better. Okay. Go. Okay, here we go. Here we go. Are we nearly there, maybe? Going from 12. Should be going from 11 to 0. We're going from 12 to 0, which means that if this is 7, let's swap these two around. Do that. If this is 0, do that. I think this is still broken though, isn't it? Because we're going to miss the next bit. Oh, made it unhappy with an unknown error message. Okie dokie. I don't currently like what's going on. I'm going to change these individual fields for just a shift register which we put stuff in. Data in 32 bits. And I'm going to say that every time we get an RX ready doodad, we put some new data on it. And in here we're going to do data in equals cat bus rxi data in. Okay. That'll do. Okay, so every single pulse we do that. That means that we don't need to keep track of these. We don't actually need them. We're sending them off immediately via the FIFO. We will need things like the data length, so let's keep that. Here then, we just count it down. Don't need this, don't need this. We want the least significant 3 bits. So that's these 3 here. We want to send them off straight away. Just like that. And write it. Next up, we want to send the least significant 8 bits of the data input and move on to the arbitration remote flag. This, I think, perhaps should be an 8. And a lot of this is going to have to go away because we just removed the fields. DLC can stay. That's part of what we're also using to verify the end of the frame as well. This is just all wrong, isn't it? Dear me. How much of that will build and how much of it's missing stuff? Arb rem not defined. This one. Data is not defined. It's okay because actually we've got something else we can use instead. Let's use data in. Least significant 8 bits. Why would you use, yeah. CRC. Probably come back to that at some point, but let's just ignore it for the moment. Don't even write it to the host. Okie dokie, what are we going to get? 5.5 comes through as 05, which is correct, and then 5.4, which is not correct. I think this is quite possibly the combinational versus synchronous logic stuff going on, isn't it, potentially? Does reducing that to 16-bit help in any way? Wonder if it's a timing issue, basically, is what I'm thinking. No. Alternatively, what we could do is data in and data. I'm just going to call it data buff so we can hold on to that for the moment. Oops. Data in is then going to be a signal again of 16 bits, but this time it's going to be made up slightly differently. MD combinational data in is equal to the, so this is combinational now rather than a synchronous concatenation. Don't know if it's going to help. I don't think it'll probably help thinking about it, because that is going to be, I don't think I can base it off this, can I? Because as soon as it's no longer ready, that combinational signal returns to 0. So I'm going to have to do buff in there. Oops. It's just that least significant bit. And for some reason, the high nibble is fine and the low nibble is not fine. No, that's completely wrong. Ugh, yuck. I'm pretty sure this should work, he says. I'm going to turn that down to 7, and I should expect to see that first 05 go wrong. It should go to an OA, I think. It goes to an O2. Oh, of course, because we've just lost the top bit, which is not part of the bottom 3 bits. And that's fine, that is correct. Oh, hang on. Are we actually seeing what's on the line correctly? So I've just put that back to 8. If we just watch the scope while this happens. There we go. We see a 5-5. However, I'm going to bring this back on screen because then I can see it too. What we have is one start bit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, I think that probably is correct, isn't it? Just zoom in on that. I'm going to keep this off to one side, but I will turn this one on for you lot to see. And I'm going to send a 5-5, which looks the same. And let's do AAA, which is inverted. So if we do, I don't want to do zeros because of the bit stuffing thing we were talking about earlier. I want to try and avoid that as much as possible right now. So if I do 5-5-5 again, what we see is the start bit at the front there. So if I do an F, will that work? That's only 4 or 5 bits, yeah. Okay, so we get, bring this back for you, so I can draw on it. 1, 2, 3, hang on, sample point. 1 sample point, 2 sample point, 3 sample point, 4 sample point. So this is the starter frame. And then 1, 2, 3, and then we get a high, which I don't think is quite right. And actually, yeah, look, 755 here in the address instead of F55. So what I'm realizing now, because I'm a Muppet, is that an address of FFF is longer than 11 bits. So it's 8, 9, 10, 11, 12 bits. So yes, we will see 7FF there. And if we send ourselves a 7FF address, or 7 address, we see 554. So if we do a 6, 154, 5, 554, 4, 1, 3, 5, 2, 1, 1, 5. Okay, this is a little bit of a pattern going on now, isn't there? 0. We see issues because I think of the. That should be okay actually. It shouldn't be bit stuffing at that point, I don't think. Let's ignore that. Oh dear me. Just want to check this is definitely only being set high there. It is. I'm going to give it a reset of 0, but I don't think that will change things. The thought process here is more. We've got this funny edge coming through. If I can bring this back. So do you see here? There's this bit of spike. And then there's this spike at our sample point, and then there's this spike, and then this spike at the sample point. And these ones are the beginning/end of the bit times. I think there's quite a bit going wrong here, isn't there? I'm going to put another debug pin in here, I think. And this is going to be a debug pin for the arbitration ID field. And what I'm going to do is, not there, debug arb.to equals fsm.ongoing. Right, let's get our synchronization or sync with the arbitration ID field that the FPGA is saying that we think we're seeing. But I have low confidence at the moment that we're lined up correctly. I think this 11 plus 1 could be potentially part of the issue. I'm always bad with off by 1 type errors like this. Gotta set the output enable as well. Actually, I wanted to put that on another pin. So pin debug. We're going for arb on pin 9. I'm just going to shift that over on the scope so I don't have to get a whole new thing out. Okay, so that's running. There we go. How does that look? let's have a see here. So remember, this is shifted, this is out of phase with the bit times because it's actually changing on the sample point, not the bit time, or the bit edge, whatever you want to call it. And actually this is happening too late, isn't it? That looks like it's happening in the second bit, not in the first bit, which is the starter frame. Okay, that's very interesting. Linked X cursors. No, this is VNC, unfortunately. Oh, yes, yeah, we can do that. I see what you're saying now. Do that. There we go. So we can do a bit time there. Oh, come on. There you go. That's definitely happening in the second bit, which is not correct. If we are idle... Oh, hang on. Yes, that's very true. We don't need to do a starter frame phase or state or whatever you want to call it, because it is what it is. It just is the starter frame. Oh, okay. Right, I've changed the code a bit. Sorry, I didn't show you that. And now, if we run it, oop, that shifts left, and we get O2AA now. Okay, so if we send that as a 3, we get 6AA. That's, I think, probably much better. That's shifted left 1, isn't it? 3 to 6? Yes. In that case, we need, I think, to get rid of this +1. Hoping. 355! Hey! Oh, goodness me! So 555 should come through. 555, there we go. A, that won't work because of the whole 11-bit thing, but 5AA, 5A5. Okay, brilliant. We're there. We've got the we've got the arbitration ID coming through, the arbitration field with its ID coming through. Wowee. That was painful, wasn't it? Silly little logic mistakes like that cost time. Right, okay. Now what do we need to do? We need to deal with bit stuffing. I would like to do that right now so we don't forget about it and run into it later. If, for example, we do a 7FF frame, or ID, whatever you want to call it, we get 7DF2A, blah, 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 and that's wrong. Now, if we look at the scope, you can see that we've got this this pulse in the middle of what should be just ones. And that is the bit stuffing that I was referring to. That's what we want to not have, or not ingest, because at the moment we're not dealing with it, we're just ingesting it as if it was a normal bit. What I want to do then, I think in here, I'm going to keep the last 6 bits perhaps, and just shift them through. And if the last 6 bits are all 1 or all 0, I'm not going to pulse that ready flag. And I'm going to just let it continue. What I am also going to do, I think, is move this data in register into the low level block here. And it can then be responsible for providing the data that the other module looks at. I'm going to make it wider again, so it's 32 bits. RX data. Right. Idle. Okay, so in the idle state, we're just going to be clearing the data all the time. Clear, 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 clear. Bit phase 1. once we've hit that trigger point, we're going to shift a bit into it. Oh no, we can't do that. Because that's going to shift in the stuffed bit as well, which we want to not present to the user. So I'm going to include a raw RX raw here. And it's 6 bits long, and that is going to include. So MD sync. Okay. So that RX raw register will see the stuffed bits as well, but the RX data register exposing up here I think will not see those stuffed bits, and that would be quite nice. So RX raw equals, and then we're going to cat. Can I do this out of my mind, do you think? Out of my brain? Self.bus.rxi. I think we need to invert it. No, we don't invert it. I'm not trusting myself. I'm just going to copy it. So there's a new bit coming in, and then we take RX raw to the end, -1. There we go. Okay. So having done that, we now need to have a look at it. And I'm going to call this bit phase, or bit phase inspect, I don't know. Well, we can name them nicely later. No, I'm wrong actually, aren't I? Because of how these bits stuffed bits work, we don't actually need this raw signal here at all, because we can look at the existing signal, and if there are 5 bits that are all 1s or 5 bits that are all 0s in the least significant bits, then we can just not clock the next bit in and carry on the state machine. So if self.rxdata 0 to 5 equals will that work to check the history? Yes, I think that's yeah, pretty much what I'm going for. So I'm going to go for OX1F or equals OXO. So if it's all 1s or all 0s, then don't latch it in. Pass. Otherwise we do bring it in, and we also then assert the RX ready pin. Self.rx data. Oops. Don't want the inspect anymore. I want to move this up there, and in both cases it goes through. Alright, let's invert this. If it's not that, and it's not that, then we can do this. Let's also say we clean that up a bit. LSB5 signal. I think that'll do nicely, won't it? 0, 0 and 1F, just because I like doing things a different way around. Okay. Yes, that's good. That should have resolved that completely, I think. Now we want to use that new RX data in here. So we don't have an RX data there anymore. Or data in, sorry, it was called. Data in, don't need that because it's being taken care of for us. RX really won't be pulsed or strobed unless we actually have something to do. And here we do RX data. Okay, let's have a look, see if this is good. Doesn't work, data in not defined, line 231. Line 88, what was that? RX raw, oh, right, yep. Never cleaned that one up. Extra parentheses. Yes, you're quite right, I meant to do that. Thank you for pointing that one out. I quite agree that extra parentheses are always a good idea. And that might even be the error that was thrown up just now. Happy days. Hey, okay. Do we now see an address of 7FF? We see nothing at all. Okay, that's upsetting. Why do we see nothing at all? Low level. So the RX trigger okay. I think in that case, perhaps we need to put a pattern into the RX data because we're setting it to 0 in the idle state, and then the starter frame is also going to be a 0, and it's already all zeros. So we never get this RX ready event, which is what I think we're starting out on here, RX ready. So I think we need to put a pattern there. Let's do a pattern of just 5. Oops. Hey Rod, by the way. Good of you to join us.
Just snatch them all up.
The CAN PD, oh sorry, the USB PD stuff is coming along nicely. I'm going to turn this off for a sec. Why is it not working? 7DF28. Okay, so it does work, and we still operate correctly with the RX data coming from the low-level module. That's no worries. Nice to see you at least. Thanks for coming.
But I quickly found out that I am not original or creative. I can't make up a new thing.
I'm going to change this one to RX trigger, I think. And that can be responsible for bringing us out of the idle state over there. Not quite what I would like to do.
Get over that. Sounding good is easy. Just borrow. Basically.
I think it should be possible to test them both at the same time. If it's not all zeros and it's not all ones, can I do OB in here? No. Oh, I can. Ooh. Don't know if Python's actually going to like it or not. 1, 2, 3, 4, 5. Oh, do I need to make the const? 1, 2, 3, 4, 5. I can do underscores? You're joking. No, well, Vim doesn't like it at least. It does seem happy, doesn't it? Or happy enough. And it didn't rebuild it that time, I don't think. Which means that changing it from hex to binary, I like the highlighting, I'm afraid.
And also be respectful.
Let us...
Make a little note saying thank you very much.
What are we trying to do right now? We're trying to get it to trigger. It is not triggering. For some reason. We see it on the scope. And that all looks okay. But the applet's not going for it. Just test, yeah, okay, that's a good idea. Let's just do that. So get rid of the zeros, because the 0 is the starter frame, and that's potentially going to be part of the issue. Oh, hang on. It's never going to get out of that state, though, is it? What? That was unexpected.
It's easy to churn out some songs if you have.
Okay, and the data's all offset now as well. 2AA instead of 555. But we can come back to that, I think, can't we? Now, okay, I think the issue is that the starter frame is causing us problems. I think we need to count up from idle. We need to count up until we've received 5 bytes, and then we can start considering the past data, can't we? Range 5. So if we set that to 0 to begin with, and here if we say, this is getting a bit complex now, with m.if, let's be 5 count is greater than, if it's less than 5, just always do it. I'm gonna make yucky logic for a sec, and then I'll come and fix it up. Else, if I think that's probably correct, isn't it? And we then need to increment it. Actually, we can put that in here. Oh, hello everybody! Very good to see you all. Thank you, thank you. We are currently working with Glasgow. So we are playing with a Glasgow and a CAN add-on board that I designed a while back. And we're trying to get it to work, and I'm having some problems with my brain. Thanks for joining us, Scotty. Bringing everyone with you. So yeah, Glasgow CAN, and at the moment we're trying to deal with bit stuffing. So I'm not sure how familiar anyone is with CAN, but what you end up with on the line is this. And because of how it tries to be quite a reliable protocol, you end up with situations where multiple bits of the same value in a row are actually in invalid state or an illegal state. So you get this bit stuffing going on here. So if you wanted to transmit 6 zeros in a row, you actually need to insert this 1. And just removing that 1 and playing nicely is part of the issue that we're trying to work out at the moment. So thank you everybody for joining. Hope it's interesting. Please feel free to ask any questions. It is icky, yes, I'm afraid so. Yeah, if you have any questions or if you have any input you'd like to guide me, please feel free to comment. And we'll see if we can get through this. Currently we're just working with the address field, so this arbitration field up here, it contains an 11-bit ID, and we're not looking at any of the rest of the frame, we're just looking at this at the moment and trying to get the bit stuffing handling correct. So the state we were in just before you all joined was that we were just considering the last 5 bits that we'd received and trying to see if it was all ones or all zeros, and that's what then triggers the bit stuffing. But the issue was we weren't actually considering the fact that we hadn't seen as many as 5 bits yet. So hopefully, we haven't tried it yet, but hopefully that might help us out. So if we rerun it, something wrong somewhere, there it is. Hopefully if we if we rerun it and we can type correctly. Okay, lots of people are trying to drive this. Oh, that's wrong. Sync. There we go. Okay, now if we try and send a frame ID, so we're done down here. We're just trying to send onto the CAN bus frame ID of 555 and then a 2-byte payload of more 5s. The reason we're using 5 is to avoid the bit stuffing, but now, oh, that doesn't work at all, does it? Now, if it works, then we're going to try start using other IDs like 7FF, for example, which is all ones, which should incur quite a bit of bit stuffing. So this didn't work. Why did this not work? I'm just using yucky logic at the moment to try and make it happen, and then we can tidy it up once we're happy with it working. What have you all been playing with over with Strange Parts tonight, or this evening, or this afternoon, or whatever time it is with you? Oh, your Vim chops. I'm afraid I run a pretty basic Vim. Vim is awesome. Quite right. Okay, so what we're doing is we're receiving bits, and while we haven't got 5 bits yet, we're taking this alternate path. Hey Matthews, 2? You have a question, why electronics developers always use Windows as their platform? I think actually that's not perhaps as true as you might think. Quite a few of the community in the 1-Bit-Squared Discord use Linux. I personally use Windows because I've kind of grown up with it. Everything I do, though, okay, Windows is my terminal, it's my desktop system, but pretty much everything else I do is on Linux. The major reasons I run Windows is so that I can use tools like Altium, which is an EDA, electronics design, package. So you can draw out PCBs and schematics and things. So that's my major reason for sticking with Windows so far, but might change, you never know. Just realised I've got some things open I should close. So yeah, I'm not sure if you have Matthews, if you have an opinion or a feeling for what you prefer. I guess it's probably Linux, but based on the question. Possibly Mac, maybe. It's got better plug and play support. And the occasional game works nicely, and I don't know, I just find myself quite comfortable in Windows. I've grown up with it, if that makes sense. I've used it for so long that I have all of these sort of workarounds for the things that annoy me in place already. And if I was to jump over and start using Linux or whatever for my main machine, especially for the UI, I feel like I'd have to relearn all of these workarounds. Yeah, I used to work for a Linux embedded sort of software consultancy company, and the entire Linux team had Linux on their PCs, but they also then had VMs so they could run Microsoft Word and things like that. So what is not going right here? We're getting 1 byte through and then it's getting stuck. So if we remove this again, it works, but the bit stuffing obviously doesn't happen correctly. We need to rebuild it, run it again. And there's, oh, it's out of phase again. That's annoying. We can come back to that in a minute though. So we're looking at the first 2 bytes that come through. So here we got 2A9, and that is 553 that's shifted left 1 bit. If we just go for 553, take that and shift it left 1. The reason that it's not AA6 and it, oh, actually that's a 6, not a 9, interesting. 553. Oh, hang on. No? Where's that 9 coming from? Maybe we should fix that quickly now. I'm going to pop that into a new state. By Tekker Jamedia. Thanks for joining us. Right, will that resolve the bit shift issue? Yes, 555, 553, 552. Okay, now if we try and send a 7F, or 7FF, sorry, ooh, we get lots of yuck. 7DF. And you can see on the scope as well that where we should have all zeros or all low or all recessive on the CAN bus is actually got that pulse in the middle of it. That green bar at the top shows us the arbitration field. So this is the bit stuffing again. We can come back. Let's just write it afresh. I think that might help potentially. What have I done? Okay. First up, MD sync LSB 5 equals, and then we're going to squish the next bit in. Oh no, not self. LSB 5 minus 1. So having done that, we also now want to see if we have all ones or all zeros. Durand, you're asking about when you're starting the applet, you'll see the port A, B voltage set to 5 volts. So port A and B can have 2 independent voltage levels, but not IOs on the same port. Yeah, that's correct. What you have, if I show you this view here, the 2 ports, A over here and B here, they have 8 IO pins each, and they also have a voltage supply. The supply rail, which we're setting to 5 volts here, supplies the voltage level for each of the IOs, and that can be between 1.8 and 5 volts, and you can have a different level for each port. Yeah. Keystorm, you found out about the web interface on your oscilloscope. That's awesome. You might also like to try VNC as well, which is what I'm using so that I can see it, because it's on my other desk for electronics desk. And for you all to see it, I'm using HDMI. So it's got a nice refresh rate that previously it's been a bit slow. Unfortunately, capturing with HDMI does mean I can't point at it with a mouse, which is a bit frustrating. Right, back to the code. If the LSB5 equals OB 5 bits, then pass. VNC, yeah. VNC is, so that's what I'm using so I can see it. And unfortunately, I've got the Agilent MSO 2000 series, and I think some years after I bought this, the 2000T came out, which allowed touchscreen, and I suspect that these become clickable with that one. But yeah, the soft keys unfortunately have to get up and go over there. But the web interface on the newer firmware is actually HTML5, which is kind of cool. So we can just have a quick play with that if you like. So browser control, remote front panel. It's pretty slow. I mean, it's not super nice, and these things aren't clickable. Oh, they are clickable. Ooh! That's a new thing from the firmware update I did the other day. Yeah, so you can change the oh, it's fine. That's why it's going so slowly. Yeah, you can change all of the various settings here, which is kind of cool. But it's really quite painful to use, unfortunately. Whereas the VNC gives nice update rates, but again, you can't interact with it. And then HDMI capture is kind of the ideal, I guess, for showing everybody else. There you go. Anyway, if it equals, right, because we're using NMyGen, it's a single equals here, which could have been part of our problem previously. Now here, I want to go to bit phase 2, so we get that ready pulse. Whereas here, I want to go directly to bit phase 3, so we don't get the ready pulse. I'm not sure this is going to work though. Okay, the other thing we needed to do was LSB count is less than 5. And we want to do this in that case as well. In other words, if we haven't seen enough bits for there to be a stuffed bit yet, then don't even look for it. That doesn't work because everyone's trying to drive LSB5. That's sync. Ah, okay. That's not so good. LSB5 equals 0. So we're going to reset that at the beginning of each frame. LSB5 count. Oops. And we also want to increment it there as well, actually. Oh, excuse me, everybody, I will be right back. Okay, hello everybody, I am back. Right, so the counter, hopefully that'll work now. If got an unexpected keyword, LSB5. Oh, I thought we needed single equals here. No, we don't, quite right. Double equals it is. Single or, single and, that kind of thing. Okay. 555. No, 0020. Okay. Oh, and the other thing, we set up earlier on the scope, you can see there, the green line at the top, the green trace, is actually tracking what we think is the ID field in the CAN frame. Hey Omni, good to see you. So you can see here that green signal that's running high for a long time is way longer than the 11 bits that we're expecting it to be. So that's a little bit frustrating, isn't it? Let's see if we can figure that one out. I removed the LSB5 combinational logic bit because I'm actually setting it synchronously here. So Omni, we're trying to deal with bit stuffing now. We've got the ID field coming in nicely, which is awesome, except when you have too many ones or too many zeros, and then you get the stuffed bit in the middle of it. So we're trying to deal with that quickly before we go too much further. Yeah, so at the beginning we set the LSB5 to 0, we set the LSB5 counter to 0, and then for each bit phase, once we cross this threshold, we move on to the next phase, and this is the sample period or sample point. On every single bit, at every single sample point, we bring in the most recent bit into the LSB5 register so that we can inspect it later. If the counter is less than 5, then this is always going to be a good bit, so we keep it. If the counter is greater than 5 and LSB5 is now all zeros or all ones, then we go directly to bit phase 3, which is not really a great name for it because the phasing is actually part of the CAN spec. So they have this time quanta. Where is it? Here it is. So they have this time quanta thing where you've got the start of the bit time at the very, very left here. You then have time for synchronization and propagation of that signal through the network. And then on the right-hand side here, you have phase 1 and phase 2, which allows you to move that sample point backwards and forwards, depending on various things about your CAN bus that you might want to move that for some reason. I've never had to move it, but I've not done loads of stuff with CAN. So with the UART, for example, you might sample at the middle of the bit time, but CAN is per spec is actually pushed it off to the side. And actually dealing with that is something that we're trying to get working right now. Dealing with the sample point off to the side is something we've done already, and that's why I said that bit phase 3 is not a great name, because actually phase 1, phase 2 are here. So phase 2 will allow us to pulse or strobe the RX ready signal, which means that we can then advance the logic over here on the right hand side. We can probably revert that to RX ready, can't we? How does that work out? Hard crash drop stuffing. You like stuffing in Turkey? That's where my mind goes, I'm afraid. Turkey. Oh, okay, that's not working at all again. Let's keep that then as RX trigger. So the RX trigger signal is actually directly tied to the bus input here. That's an interesting point. That's the inverted RXI. No, that's correct, yep. Bad Thanksgiving. I'm sorry. So yeah, reverted that RX trigger and run it again. Hopefully we'll get something happening, but I expect it'll still be wrong. So we can watch the scope in a second, hopefully. Ding, 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 there you go. It is wrong, and we see the wrong data coming through. So if we come back here, why is it wrong? Where's the logic going? Duran, no worries. Thanks for joining. I'll hopefully see you again soon. I'm going to take a moment to have a little bit of water. Okay, a bit more water actually. I think this logic all holds together. If anyone can see a problem, please feel free to shout. We could put a signal on the LSB counter just to make sure it's actually getting up to 5, couldn't we? And then watch that with the scope. Let's do that, shall we? So I'm just going to make a debug signal, and I'm going to say self.debug equals lsb5 count equals greater than or equal to 5. Actually, no, let's make it less than or equal to 5. I'm expecting to compare the lsb5 without the current bit in it. Yes. I think so. If we look at the bit stuffing diagram here, I have to zoom in again, you get, oh, that's a very interesting point actually. Some things don't get stuffed. I think it might just be the CRC actually, which is not stuffed. And various other bits. So maybe all of this is stuffed. Should we just refer to the spec quickly? Okay. I think it's part B. No, maybe not. Oh, I don't like these specs. Bit timing requirements. Stuff. Bit stuffing. I'm only really planning on getting one bit out via the scope for debugging, and I want to see that it gets to 5, I think is my big thing. I just wanted to finish checking about the stuffing. It's probably not going to say something, is it? 6th dominant bit violates the rule of stuffing. Yeah, so 5 is the maximum you can have. Starter frame, arbitration field, control field, data, and CRC sequence are coded by the method of bit stuffing. The remaining bits of the data frame, remote frame, CRC delimiter, ACK field, and end of frame are of fixed form and are not stuffed. The remaining bits of the data frame. I'm going to move that over here and come back to the diagram quickly. The CRC delimiter is not stuffed. The ACK field and end of frame are not stuffed. The ACK and end of frame. Oh, okay, so all of this is just not stuffed. Well, that's okay. Can I use the logic analyzer thingy? I probably could. I didn't have great experience with it last time I tried it, which is why I tend to reach for scope or logic analyzer rather than the internal analyzer. I think it was missing a bunch of signals and I couldn't quite immediately figure out how to get the other signals, so I sort of ran away from it. I'm just going to do this one for now, I think. So yeah, I think we figured out which bits need stuffing and which bits don't need stuffing. I'm going to add this now to the debug pads that we've got going, and I'm going to put it on this one. ll.debug, and I'm going to move that across on the board. Oop. And that back on. Oh, I know the data's wrong, isn't it? Yeah, okay. Well, that's interesting. It seems to be high all the time. What does this device do? Good question. This is a Glasgow Digital Interface Explorer. Is this board here? You may have seen it around. I will shamelessly pop a link to the crowd supply in the chat. It's now been funded and it's available for pre-order. This is a Glasgow Digital Interface Explorer, which basically has an FPGA and a USB chip on it. And on the other side, in the PC, you then have a whole lump of Python and NMyGen, which is a way of describing logic, which then gets put into the FPGA. And in this particular situation, we are connecting the Glasgow itself to a CAN add-on board that I've built so that we can interface with CAN circuits or systems. And currently we're working on the bit stuffing aspect of CAN. Good question, Hard Crash. Does LSB5... Yes, you're quite right. That needs to be a 5 width signal, doesn't it? Do you think that's the only problem? Yeah, it might be, because that might match 0 a lot, mightn't it? Anyway, okay, where were we? We were trying to deal with that debug signal, which looked a bit wrong. We've made that 5 bits wide now instead of 1 bit. Purpose of the system as a whole. Well, Glasgow as a thing is a big project which allows you to interface with almost anything, is the idea. So you can connect to, for example, UARTs with an unknown voltage, unknown baud rate, that kind of thing. You can connect to, in this situation, we're trying to interface with CAN, get that working. You can do servo control, you can do all sorts of stuff. That is a very good point about implicit widths. Yes, we could make that a const with a width as well, couldn't we? Let's just do that maybe. A const that of type unsigned 5. I'm actually a bit surprised that it didn't say LSB5 could not ever equal 11111. You can indeed, Exabean, yes. Can it interface with a smartphone? Not officially, but White Quark has had a Glasgow connected to an Android phone and the software component of Glasgow running on that Android phone. So that's pretty cool if you ask me. In terms of interfacing, are you referring to can the smartphone control it? Or are you talking about can it help you debug a smartphone? Or, you know, connect to and talk to a smartphone? You tell me. Yeah, this is just wrong, isn't it? So, yeah, I mean, the Glasgow itself is, this board here connects via USB to a PC, and using that USB connection, you program it and you get data out of it. So, for example, you can connect it to an I2S audio interface, that kind of thing. In terms of this connection here, you can connect that to a smartphone and unofficially get that working there. But in terms of these interfaces, which is what we're working with sort of at the other end to connect to devices in inverted commas, I don't think you probably have much success talking to a smartphone based on what they are these days. They're quite complex. Oh, Glasgow can do a lot of things. Yeah, I just said a couple. It can do JTAG, it can do I2C, it can do SPI, it can do single frame parallel bus, parallel images. It can do, there's a massive list. If we run, I will show you here. If we do Glasgow run help, it's got a big list. And this list is sort of everything that it will support immediately. You've got, as someone said already, you've got floppy control, proms, you can do PS2, JTAG of various modes and operations. You've got I2C, SPI, UART. We're working on the CAN sniffer now. You can do various sensors. I've been working on a Hub 75 panel interface for it. You can do WS2812 LEDs, you can do VGA output, test patterns, that kind of stuff. So it's very cool. It's very flexible, and there's so long as your signals are TTL or sort of 0 to NX voltage, so you can go from 1.8 to 5 volts. Differential and high-speed signals are not really possible, but so long as they are less than about 100 megahertz and you don't need more than about 16 signals, then you can probably interface with it. It's that flexible. Right. So that never reaches 5. Why does it never reach 5? Let's do equals 0. Oops. Okay, so it's now 0. Let's do equals 1. This is where the nice analyzer will be good, isn't it? Yep, it is Python. NMyGen is what we're actually writing. So this is Python, but all of these mdcomb, m.fsm, m.if, all of this is NMyGen. And that's another tool or another framework, NMyGen. And I'll put a link for that in the chat as well. But it's kind of a new way of doing FPGAs, if that makes sense. A new HDL. It's quite a lot easier to reason about, generally speaking, than things like VHDL or Verilog. And what's nice as well is that this is everything you need to run the Glasgow interface is in this one Python file, which is awesome, and that includes the FPGA stuff as well as the Python, the PC side stuff. AGL, I meant to say HDL, so a HDL, hardware description language, I think it is. Hardware description language. It allows you to describe the logic of a system, the and and or and how things are wired and everything like that in code, basically, instead of wiring up things. And you can then compile that down into a bit stream, which you then load into an FPGA. Right, so debug SP is pin 8, which is what we're connected to. And that is showing us when the counter is a value of 1. There we go, so it's a value of 1, and that looks correct. Does it ever get to a value of 4? Where does the counter get incremented? Here. So while it's less than 5, it goes up and up and up, and then it should max out at 5 until it gets reset at the next idle state. 4 is good, yeah. Okay, does it ever equal 5? Lethal error. Are we testing the pins on the port? Can you expand on that? Oh, yes, it does go 5. Okay. Well, that's good. And if I run it again, it's still 5. It never gets reset. It never goes back to idle, perhaps. Which state is idle? Why don't you make it go back down? The green wiring, you talking about the scope trace that I'm flashing now? Why don't I make it go back down? So I was planning on making it come back to 0 in this idle state. And the idle state should be you should get back into that idle state when we are no longer asserting the RX run flag. Oh, yes, that's a very good point, Omni. Well done. Testing you. The green trace on the scope is the debug signal that we're currently sort of working with to try and get a feel for what's going on inside the FPGA. So I think actually that is part of it. I think the other thing I noticed or realised is that we may never be releasing the FPGA. So here we go. While we're not idle in this state machine, which is a higher level one you can't actually see, there we go. We maintain this RX run signal. So what I think I'm going to do is put mnext equals idle here, and that should let it stop. And once it's stopped, it can just ignore the rest of the frame or get garbage or whatever it wants to do. Lethal, that's fine. I'm sorry, I don't mean to be dismissive. Feel free to ask questions if you have any queries of what's going on or you don't understand or follow. So yeah, the green wire or the green trace on the scope is, if you can see on the left, there is the little symbol there with a 2, which is also in green on the far left, and that will that shows you the reference point, so the 0 volt point for that signal. And at the moment it's high, so it's up and above that signal, and that just means that it's got a logic value of 1. So when we're trying to debug things, we can set a logic value of 0 or 1, and it's a very simplistic way of dealing with these things, but it allows us to have some kind of some control or some insight, whatever you want to call it. And yeah, as Hardcrash, it's a very basic form of printf. You might find people blinking LEDs or wiggling signals like we're doing right now. So that signal you can see goes up and then it comes back down again, and that should frame, I think, the arbitration ID, and so it does reset nicely now that we're actually letting it reset. So that's good. The trouble is then it keeps starting again and getting more. Yeah, that's correct. Lethal error, sorry, yeah, that's correct. Okay, now if we have a look at this and we send a new frame AAO2 554, trying to understand what's actually going on here. Maybe we need to reset it somehow. So I'm just going to force trigger. There we go, so it's all clear, we can see what's going on nicely. There we go. The debug signal is still LSB count equals 5. Clicking buttons, yeah. So we've got the starter frame, we've got 0, 1, 0, 1, 0, 1. And actually if we go 1, 2, 3, 4, 5, 6, 7, it goes high on the 7th, which is unexpected. It should be on the 5th, I think. The HDL, so the hardware description language, describes the logic that's running inside the FPGA, and that logic that then gets set up and executed effectively will then wiggle that signal, turn it on and off, that pin, based on various other states within the system. Yes, yeah. So I thought LSB count greater than 5 is only for the 5th bit of the whole transaction. I thought CAN was 5 volt. So yeah, what we're trying to see is when we have observed at least 5 bits in a row, the 6th bit would then be illegal if it was the same as the previous 5. So if we see 5 bits, 5 zeros, we then need to stuff it with a 1. If we see 5 ones, we then need to stuff it with a 0. So I can draw this out a bit in the editor. Here we go. So if we have 1, 2, 3, 4, 5, we then need to stuff it with a 1 before we can do more zeros. And if we have 1, 2, 3, 4, 5, we then need to stuff it with a 0 before we can do more. So if it happens, so this is the stuffed. Let's do raw. Okay, if that makes sense. So we've added that stuffed bit there. And this is then the stuffed one. Lethal Error. There are, as Keystorm said, there's lots of stuff on YouTube. If you want to know about FPGAs in general, then it's never been more accessible. It's a fantastic time to get into them. There are all sorts of boards and sort of dev kits and whatever you might want to have a go at to play with. So I would really encourage you to go and have a rummage. If you felt like this is actually something you really want to do, then please feel free to join the 1-Bit Squared Discord server. They are a really lovely community, quite interested on FPGAs. If I can share you this link, there we go. And they will absolutely help you. Lots of friendly people over there. The message for the frame is containing 2 bytes. It's containing 2 5s, or 5555. So we could change that to be AA if you like, but basically I'm using 5s and A's because that avoids the bit stuffing. No worries, Lethal Error. Hopefully I'll see you there. It'd be great to have more faces. Okay, so yeah. Once we detect and remove a stuffed bit, we then need to reset the counter, so that's what we're doing here. If, however, we have less than 5 bits, so if we have more than 5 bits, or at least 5 bits, and the last 5 weren't all zeros and weren't all ones, then we treat it like any normal bit. And what do we do? Yeah, we just sit there and keep going. We don't need to increment it because it's already at 5. My logic for the counter, sure. Let's walk it through. So we've got the LSB5 signal, which is 5 bits, the most recently received 5 bits raw from the bus. We've got the LSB5 counter signal, which is the number of bits in that register. So when we're in the idle state, we set the LSB5, this is the 5 bits to 0. So we reset them. Probably not super necessary. Oh, okay, Omni. In that case, I'll pause my walk through, and I'll maybe carry on when you're back. Hard crash. LSB5 is the last 5 bits off the RX stream. It is active after the 5th bit, in thus allowing the OXO or OX1F checks. That's correct, yeah. So basically, when the 6th bit comes in, if the last 5 were all 0 or all 1, we need to ignore it. That's my plan, at least. Looking at the scope, however, we can count. We got the start of frame, we got 0, 1, 0, 1, etc. And so that's 1, 2, 3, 4, 5, 6. And on the 7th bit, the debug signal then goes high. And that is supposed to be going high on the 5th bit. which is incorrect. Not entirely sure why that's happening. Not entirely sure why that's a 5 either, but never mind. I don't think that'll affect anything. Oh, sorry, you're not watching the screen. So the debug signal is going all over the place because that is actually very interesting. Sometimes it's very short, sometimes it's very long. That's not expected. It's going all over the place because we're not actually framing the signal correctly yet. So if we restart the applet and run it once, that's correct. So 0, 1, 2, 3, 4, 5, 6. That's going late. Oh, sorry, I left you off the computer screen again. It's coming up to 2 o'clock in the morning for me, so I'm thinking I might start winding up soon. I hope that's going to be okay with everybody. I'd really like to resolve this though. Go to sleep. I will do it in a bit. I'd like to spend the next 15 or so minutes just figuring this one out if we can. If we can't, then that's fine. We can do it next week. Would it be easier to keep account of the bit non-transitions and not compare with 0, 0 and 1F? I don't know about that one. Yes, we could do that. Let's give that a go. I like that. So we need the previous value and the current value. This is just trying different things until it works, isn't it? That's not ideal. Okay, so Rx last, and we want Rx, what do you want to call it, stable, count. I'm going to just make it a big signal. So these two get rid of. And Rx last is nothing. Rx stable count is reset to 0. Okay. Let's just bunch these up a bit and comment them out. Oops, that's annoying. Don't want that either. Okie dokie. If started at 1. Oh, you might be right there actually. Yeah, that's probably my off by 1 error previously, wasn't it? That's annoying. Okay. Can you measure the T on and T off of the signals? That is actually another applet that I've been working on. which will allow you to do frequency counting as well as a sort of duty cycle of signals and things. It's not something I'd probably look to do here because it's a little bit more complex, so we don't really want to care about how long the signal's on and off for. What we're actually doing here is to try and, this is hard crashes I did, to try and count the number of times the signal doesn't change. So rather than the T on T off, it's the number of bits that are the same, effectively. So if Rx last equals the self bus RXI, then we are going to increment the Rx stable count. Hard crash, not the count, the last bit. Not following, sorry. In idle, set Rx last to 1. Yeah. Does that matter though? Yes, it does. Okay, probably. Yeah. Okay. We can remove that from here as well. Then that's what you're saying, isn't it? Okay. So the last value is a 1. Start of frame is a 0. If it is equal, then increment. Else, this has got to be sync, not combination. Oops, combinational. Else we reset it to 0. We also need to keep hold of the last value. No. Like that. And now we also need to say, if it's been the same for too many times, then. Do we saturate that as well? I think I want to say I want to invert this, I think, and then I'll do that first. So if it's not the same as previously reset, else if the Rx stable count is greater than equal to 5, then we don't want to take in this data. I think that's right, isn't it? We want to ignore it. Ignore the stuff bit. So we want to ignore the stuff bit, and B, we want to reset that counter as well, don't we? Because this is the stuffed bit. We need to reset and start again. But keep the stuffing for counting in Rx last to get the reset. Sorry. Again, not quite following. So when the start frame bit is red, the counter resets. But keep the stuffing for counting in the Rx last to get the reset. Yeah, I'm not sure I follow, sorry. It should always be raw. I think I agree, which it is. You're suggesting that actually we don't need this if the bus is well behaved because it will naturally reset because the last is no longer equal to the current in this condition here. Is that what you're saying? It's a little bit awkward to do this via chat, isn't it? Oh no, I'm gonna leave it down there, I think. Or I could put it at the top. I think it's always going to be there. This condition shouldn't. It's greater than yeah. This condition should never happen if the bus is well behaved. But if the bus is not well behaved, if it sends too many bits that are of the same state or the same value, then it can happen. And maybe this is actually an error condition. Error. And maybe we should just abort everything at this point. Yeah, exactly. Greater than. So don't forget it's 0 based. So 0, 1, 2, 3, 4 is 5 count. 5 is the stuffed bit, agreed, but also this should catch that stuffed bit. So if this doesn't catch it, then it falls into here, and it becomes a naughty bus. This should be a stuffed bit, but it wasn't. Disk. So I think I'm going to leave that like that for now. I think that holds together, doesn't it? And we can now make this work on the RX stable count. If it is equal to 5, this is the 5th bit, which is the same. We should be able to trigger that via the command line. Okay. Oh no! That is very unhappy. Waggling all over the place. It's a 5-bit signal. Oh, we're never advancing state here. Whoops. So. It's going crazy, it really, really is. It's not a happy bunny. Basically, we're never getting out of this bit phase 1 state. End.next equals bit phase 2. In here, we need to do this, and that is to push the new data into the RX data register, and we need to advance, and we either advance to bit phase 2. No, we can put this into here, I think. No, we need a new one. Okay. So I'm going to say less than 5. Do that. And I suspect I'm not confident about it. You return! Welcome back, Omni. Shift? Shift? Okay, what do we reckon? Oh, look at that! So the 5-5 came through, lovely. And the green signal is low, which is perfect. So this is the 5-5-5 here. And those 2 bytes match up with the ID here. Okay, now let's try something with lots of zeros or ones in it. So we're going to go for 7FF. Restart the applet, of course, 7FF. There it is, and that's wrong. Okay. If it's less than 5, why is this never getting to 5? The 0 was red. You have to ignore this 0 if that's the one you're referring to. The stuffing's still not working, Omni, no. We're trying a new technique now. So send lots of 1s. We see 7DF, etc. Oh, actually, oh no, the trigger has worked, okay. The green line, however, is not indicating that it's ever reached that 5th value, or 5th count, whatever you want to call it. Let's put that down to 4. Oh, come on, typo. Like that. I think you need to shift if it's not equal to 5. Less than 5. Oh. Yes, you're probably quite right actually, aren't you? I'm still a bit confused why we're not seeing... There we go, there's the 4. Okay, let's put this in here. And... what do you... I think, yeah, maybe Omni. No worries though. Okay, I think this has got to be 4 because actually it's 0 based again, don't forget. Pins, posts and all that, as you said earlier. Is this going to work? 7FF. Fingers crossed, anybody? Anybody? Place your bets. Ah, 7FF! Whee! Oh, that's a good feeling. Okay, let's try another value. Let's go for 7OF. Do you reckon that's going to come through? 7OF! Whee! Oh, excitement. Let's pick another value with lots of zeros in there. I'm going to go for 401. Do you reckon? Yes. So zeros and 1s both work now with bit stuffing, which is awesome. Thank you, Hard Crash. Thank you, Omni. I think that was very, very kind of you to help me out with that one. This wants to really be an error. I need to do this. Make this blow up. Shifting data in. Let's get rid of all this rubbish then. Now, we need to remember that so the RX Ready strobe is relevant for everything up to, but not including, this. So these never get stuffed. I mean, those never get stuffed for obvious reasons. They have to be 1s, and that's part of the bit stuffing and everything. So that's that. These never get stuffed because that wouldn't work very well if you've got a CRC that ends in lots of zeros and you need to put the acknowledgement in there, then you can't, for example. So we still need... The overhead is huge? What are you referring to there? In the protocol? Well, don't forget, this is only a single byte payload. It supports... It supports up to, I think it's 8 bytes, even though it's got a 4-bit length field. CAN has lots of magical properties, and 8 bytes with no FD, yeah, exactly. So you can have 100, but you can't have 1111, for example, without the FD stuff. We're not targeting that right now. Maybe later. Yeah, I think it changes quite a lot of stuff. Yeah, flexible data rate is interesting. Differently cast. Let's ignore that. Ignore that for now. No. What I was trying to say is that these do not get stuffed, which means that we have to not stuff them. The delimiter, actually, I'm wondering if that is enough, and they are always 1. Let's see if I've got my PDF still. Here it is. Delimiter. Yeah, so I think the slots for the ACK is there. Ah, of course, okay. Now, if we had lots of 1s, followed by the delimiter, followed by a NAC, no acknowledgement, then we might start to see issues with the bit stuffing scheme that we've got in place now. So these actually need to be triggered off the timer rather than the bit stuffing RX ready. So I'm going to say there's an RX ready, but there also needs to be an RX ready raw. And that raw one always gets strobed, and the RX ready one only gets strobed if there's no bit stuffing happening. So I'm going to move this into here. I don't think this is going to work out. I'm going to remove this one and turn that down to 2. Oops. I'm also going to do that. So the RX ready raw always gets wiggled. I think we're going to have issues now with pipelining and that register being read. I don't know. I can't reason about it. So let's go for 555 again. Yeah, 2AA, not good. So the issue here is that this RX ready flag is going high while the data is still being changed. And the other side, the other state machine, is then seeing that flag and trying to do stuff with it. So I think this might be the end for today's stream. Thank you everybody for hanging around. I'm very glad that we've got the beginnings of bit stuffing working at least, because that was not cool, the frustration I was going through there. Let's undo this so that it works again. I'm going to put the ready in here, the raw, like that. I need to sort out the bit phase 2, that's a bit icky. To do sort this out. Yeah. Let's just prove it still works. Five. 1, 2, 3, 4. No, 1, 2, 3. 1, 2, 3. Perfect. 3, 2, 1. Very good. Okay, brilliant. Bit stuffing works. Let's just do the final. Was it 401? 401. Yep. So do that again. There you go. That's the 401 there, and the 7FF, which is come through well. Brilliant. Oh, very good. Well, thank you everybody for joining. I'm going to leave it there. I'm going to try and do more of this next week, I think. I might try and have a little tidy up of this code in the meantime, see if I can make it lay a bit flatter, a little bit nicer. Next week, given that we've got bit stuffing going, we've got the sample points going, I think next week we should be well on track to get the full frame coming in. Possibly looking at the CRC, that'll be a new one for me. I've not done CRCs in a long time. Not a new one, but yeah. Yeah, hopefully we can get a full CAN frame coming in, CRCs, acknowledgements, etc. coming out, and that would be awesome. So yeah, thank you everybody. I'm going to run away now and do some sleeping, and hope you're all well, hope you're all good, and see you soon, I'm sure.